It's time for Maths with Mr. Thomas.
Here we go! Chapter 13, lesson number 1, vectors, and it's a recap. Now, vectors is something that we started with in National 5, and you really have to be an expert with everything from that before you go on and do the work from higher. So I've started this chapter off with a recap of everything that we know about vectors so far. Starting with the basics, what is a vector? Well, there's two different types of measurable quantities. For example, you can measure something and it could be a scalar. So a scalar is a quantity that has a certain size. Examples of scalars, you could have time, the time taken for Sophie Boswell to win the Nobel Prize of Mathematics. Or the speed of Ryan running away from the police, speed would also be a scalar. The length of this pen, what pen? This pen, you remind me of the pen. That would also be a scalar. A vector though, what's the difference? What makes a vector a vector? Well, a vector's also got a certain size, but it also has a direction. Woo! Examples then of vectors, well, gravity is going to be a vector. There is a certain size there, depending on which planet you are on, and gravity is pulling you towards the center of the Earth. So there is a direction there. Something else? Force. The force applied to a snooker ball. If you hit a snooker ball with a certain force, well, there's a direction that is also involved. Velocity too, the velocity of a plane. Well, the plane is going to have a speed, but it's also going to be going in a certain direction. So, two different types of measurable quantities. You have scalars and you also have vectors. So a vector is a quantity that has a size and a direction. Moving on then, naming a vector. So, a vector can be named in three different ways. First of all, we need something with a certain size and direction. So we've got this line here going from A to B. You can see it has a length, it's also got a direction, the wee arrow showing you it's going from A to B, and you can name this vector in three ways. You can, first of all, name it using the letters at the end of the line segment. So it starts at A, it ends at B, so we could say that is the vector AB. And we have that wee arrow just on the top. The wee arrow is always going to be going in that direction. If the arrow is pointing the other way here, going from B to A, well here we would have BA, and this arrow still goes from left to right. We can also name it using a lowercase bold letter. So here we've got a wee u beside this vector, so that would be vector u, just written here in bold. And the third way, we can use a lowercase underlined letter, just the way I've done here. So that, you could also say, would be vector u. And this is how I'm going to write them for this chapter. Moving on, we then looked at multiplying a vector by a scalar. Woo! When multiplying a vector by a scalar, remember a scalar is just going to be a number, then the direction remains the same, but the magnitude or the size will change. So let's say we have a vector u. We can see here it's a certain length, it's a certain direction, and from there you could sketch 2u, or 3u, or negative u, or negative 2u. So if you want to sketch 2u, well, as it says here, the direction remains the same, but the magnitude or the size changes. So sketching 2u would just change the size. So it's going to be 2 times the length of u. You can see here, from here to here is about 1u, and then from here to here is another u, so that's just going to be 2u, and the direction remains the same. 3u, how do you think that would change, Connor? Yeah, it's just going to be 3 times the length. Good. So you would have something that looks like that. So direction remains the same, but the size is going to change. What about negative u? Brilliant, well done. So for negative u, it would also be parallel to u, but it's going to be going in the opposite direction. So the size remains the same, but we're heading in the opposite direction there. Negative 2u, I'm sure you can guess from that one. Well, the negative means you're heading in the opposite direction, and the 2 is going to double the size. So you would end up with something like that. And make sure, if you are sketching them, you do have this arrow drawn on as well to show which direction your vector is heading. From there, adding and subtracting vectors. The main thing you need to think about when you are drawing them and you're adding and subtracting is you have to add them tip to tail. So let's say we've got two vectors. We've got vector u, this length, this direction, and vector v, which is this length and this direction. If you are having to sketch u plus v, well, it says here you add them tip to tail, in other words nose to tail. So where one vector ends, the other one is going to start. So if you're adding u plus v, you can see here, we've got vector u, it's the same length, same direction, just as the u here. And then where we ended writing that u, then we draw this other vector v, and it's got to be the same length, same direction. You can see there, we're putting that on. From there, we started here, we came up here, we then drew v, and really the shortcut is going from the start to the very end, so you could just draw that line in there, and that there will be vector u plus v. So it's the shortcut really from the very start to the very end. What about subtracting vectors? How would we subtract them? Well, again, you've got to add them tip to tail, but to subtract them, really what you're doing is you're adding the negative. So let's take those two vectors again. We've got vector u and we've got vector v. So if we have to sketch u minus v, well, really what we're doing, as it says here, we're adding the negative. So we've got vector u plus negative v. And negative v, how would you sketch negative v, Erin? Good. It's going to be parallel, but it's just going in the opposite direction. So the first thing you really want to think is, well, negative v is the same size, but just heading in the opposite direction. So that there is negative v. So if you are sketching that, you would start off drawing a vector u. So there is vector u drawn in, and then we're adding negative v. So negative v is going in this direction. So we can just add that on the end of u. So they are added nose to tail, or tip to tail. From there, to draw the resulting vector, you're thinking, well, I'm starting there, I then came up here and along here, that's where I finished, just drawing the shortcut. So you're going from there to there, and it will be going in that direction, as you can see. After that, we then moved on. Something else we did was looking at the components. So we can represent vectors on a grid system. For example, let's take these vectors. They are shown on the grid. So on this grid here, we can have vector a, b. So you know, if we're going for vector ab, going from vector, this vector here, going from point A to point B, well, really to do that, you would have to go along 4 units, and then you're going up 3 units. So that is written 4, 3, and that is your vector. On the top, we've really got the x value, and in the bottom, we've got this y value. So you're going along 4 in the x, and then up 3 in the y. For vector CD, going from C to D, well, for this, you would have to think about the x, you would have to go back 4 units. So at the top, we'd have negative 4, and then after that, well, we're going down 5, so we'd have negative 5. For EF, going from E to F, well, if we're starting at E, again, think about the x, then the y, so going along, first of all, we're going back 3 units, and then we're going up 1 unit. So we'd have negative 3, and then because we're going up 1, it's just positive 1. And final one, let's say we're going from G to H. Well, from G to H, we're starting at G, and in the x going along the way, first of all, we're coming along 1, 2, 3, 4, 5, 6. So it's going to be 6. And after that, if we come along 6, we've then got to go down 1. So we'd then have negative 1. And this is referred to as the components of the vector. It's the numbers, it's the x and the y that you would have. Once we have it in this form, well, what we can do with them is we can add, subtract, and multiply vectors by a scalar. For example, if we have a and b written in component form, vector a is negative 2, 5, and vector b is 4, negative 6. So we could evaluate, for example, a plus b. So to add your vectors together, well, we've got vector a, which is negative 2, 5, and we're adding on vector b, which is 4, negative 6. And to add them, really you're just adding the x's and then adding the y's. So negative 2 add 4 gives you 2, and 5 add negative 6 gives you negative 1. It's as simple as that. Subtracting is going to be the exact same. We've got this first vector a, but we're taking away vector b. So instead of adding, we're subtracting. So it's negative 2 take away 4, and 5 take away negative 6, which will give us negative 6, 11. Woo! From there, 3a, well, we're multiplying vector a by a scalar. We're multiplying by 3, so really it's 3 times vector a. And to work that out, then we just do 3 times negative 2 and 3 times 5, so that'll give us the vector negative 6, 15. To divide, well, really we're multiplying by the fraction, would be multiplying by a half. And dividing by 2 is multiplying by a half. If we've got the negative in here, multiplying by negative a half, well, it's negative a half times vector b. For that then, well, negative a half times 2 and negative a half times negative 6 will give us the answer of negative 2, 3. Moving on, something else that we looked at was position vectors. So if we are given 2 points, for example P and Q, we can find the vector adjoining them as follows. So here we've got our x and our y axis, really. We've got our P and our Q. We've got these 2 points. So what we want to think about is the vector going from P to Q. Well, really what you want to do is you want to think to go from O to Q. So from the origin to Q, well, that vector minus the vector from the origin to P. So putting in the numbers there, what that'll give us is from O to Q, we're coming along 5 and we're going up 2, so that's a vector 5, 2. For OP, that's going from O to P, from the origin to P, that is going along 3 and up 4, so we have 3, 4. If we subtract them, 5 take away 3, 2 take away 4, would get 2, negative 2. And you can see that that works out. Going from P to Q, you would have to go along 2 in the x and then down 2 in the y. So that would be 2, negative 2, which is what we get here. Really, in general, that works for all position vectors. To go from P to Q, you take vector Q and you take away vector P. For example, if we have A and B with negative 4, 1 and 5, 6, we want to find the components of the vector A, B. To do that, well, if you're working out AB, then it's going to be B minus A. So vector B, to go from the origin to B, that is the vector 5, 6, going along 5 in the x, up 6 in the y, and we're taking away vector A is negative 4, 1. So we'd have negative 4 in the x and 1 in the y. If you subtract them, then you would end up with 9, 5, which means then the vector to go from A to B, you'd be going along 9 in the x and then down 5 in the y, so it gives you that vector 9, 5. After that, something else that we looked at was the magnitude of a vector. And the magnitude is really the length of the vector, or its size. And the way you write it is by using these modulus signs, or the magnitude lines. So, to work out the magnitude, I'm sure you remember last year you worked it out using Pythagoras. So, if we have the vector from P to Q, if you imagine it with your wee right angle triangle drawn in, you're coming along some value in the x, you're going up some value in the y. So here you can see you're going along 4 boxes and up 3 boxes. So you could use Pythagoras with 4 squared plus 3 squared and then square root it, and that'll give us the length of this line. The way that's written though is you would say the vector from P to Q with these modulus signs, which means the size of that, and that is also known as vector u because we've got a wee u beside that, and it's the square root of a squared plus b squared. For example, if I want to calculate the magnitude of the vector joining E and F, well, the first thing I would need to do is I would need to work out the position vector from E to F. So doing that, EF, remember from the last page, it's going to be F minus E. Vector F from the origin to F is going to be 9, negative 13. I'm taking away E, which is 3, negative 5. If I work that out, I would get 6, negative 8. So that is the vector EF. What I then have to do is to work out the magnitude of that. So the magnitude of EF is the square root of 6 squared plus negative 8 squared. Work that out, it's the square root of 100, which will give us 10 units. And that would be the magnitude. Something else we then looked at was alternative vector journeys. So for example, this trapezium here has EF, so there from E to F, parallel to HG. So these two lines are parallel, and the length of HG is 4 times the length of EF. Vector EF, I'm going to call that just vector A, and vector EH, I'm going to call that vector B, so this line here. Points M and N are the midpoints of FG, so there is point M, and midpoint of HG will be N. So in terms of A and B, so using these two vectors, write down the values of, let's go first of all with HG. So I can see from H to G, well, for this you know vector EF is A, but it tells you here in the question that this is 4 times the length of EF, which means then that this will be 4 A's. So in other words, 4A. Remember, your vectors, it's got to have the same length, same direction. So this length here is A, so if you have that, then A is going to be ending up here, and you would really have 4 of them. So it'll be 4A. If you want vector EG, going from E to G, well, to do that, you have to think about what would this vector be. But you can only go along these lines that really you know. So you could go along from E to F and then up here, but you don't know this vector. So think about this. You could also go up here to H, which is vector B, and then you could go along from H to G. And we just found that vector HG is 4A, which means then to go from E to G, you're going up here to H, which is vector B, and then you're adding on HG, which will be 4A. So that will be that vector EG. To go from E to N, there's E there, there's N there. Again, you want to think, how do I get there using these lines that you know? So to go from E to N, well, you'd have to go up first of all to H, which is vector B, and then you're adding on, well, remember HG is 4 times the length of EF, but because this is the midpoint, well, that's going to be A, and then another A, so that's just 2A. From there, you could work out FG as well, to go from F to G. Well, you can't just go up this line here because we don't know the vector for that, so we'd have to find some alternative journey. So you could go back the way to E, but because that's going back, vector A, it's going to be negative A. We're then going up here, which is vector B, and then you're coming along from H to G, which is going to be 4A. If you simplify that, then we've got negative A into 4A, which means then we'd have a 3A. And we've also got this vector B. You could also write that backwards with 3A plus B, or just leave it as B plus 3A. It makes no difference. To go from G to N, so here is vector G, here is vector N. Well, remember, this HG is going to be 4 times A, but because this is the midpoint, we know from N to G will just be 2A. But we're not asked for that vector, we're asked to go from G to N, which means we're going back the way, so we'd have that as negative 2A. And the last one, if we're going from M to N, well, to go from M to N, well, we don't know the vector for M to G. But what we do know, though, is, well, earlier we wrote down the vector from F to G. So here is the vector from F to G, and because M is the midpoint, we know it's going to be the half of the vector from F to G. So we've got half that vector, so we've got half FG, plus, and then again to go from G to N, well, you would have that vector there. Half FG is going to be half of this answer here. So it's half of 3A plus B. And then we're adding on, and vector Gn is negative 2A, as we just saw in the 5th part up there. From there, if we half the 3A, we'd have 3 over 2A. Half the B, we'd have half B. And if we're adding on negative 2A, we're really just taking away 2A. Simplify that. 3 halves A take away 2A will give us negative a half A. And we've also got that half B. So that would be our answer. Really, everything that we've done so far has been in 2D, and that, I imagine, is how you would have started vectors. But what you found was you can also flip it to 3D, and all the rules still apply. So here, we can represent points in 3 dimensions instead of just 2. So here is point P, and it has the coordinates 3, 2, 5. The 3, 2, 5 means you are coming along 3 in the x value, you're going back 2 in the y value, and then you're going up 5 in the z axis here. The red line shows a 3D vector indicating the position of P from the origin. So if you think about it, if you were going from the origin to P, well, that would just be this vector here, shown in red. And you are going from the origin to P, so it's going to be in that direction. The position vector then is represented by, well, you need the x, the y, and the z coordinates. It's the components that you are using. So you can say from O to P, that is vector P, and you would have to go along 3 in the x, 2 in the y, 5 in the z, so that's just 3 2, 5. And that is how you would write that. The good news is that everything we have learned in 2D can also be applied to 3D vectors. So if you are given a couple of vectors there, well, you can add them, you can subtract them, you can multiply by the scalar. You could also work out AB. Again, the same thing, it's just going to be vector B minus vector A. So it'll be the 5, 6, 3, take away 2, negative 1, 4. If you subtract them, it's the same rules. Subtract the x's, subtract the y's, subtract the z's, and you would get this position vector. You could then go on and you can work out the magnitude as well. The magnitude is the square root of, and here you'd have negative 7 squared plus 7 squared plus negative 1 squared. You've just got that extra number when it is in 3D. So that'll give us a square root of 99, which you can then write as root 9 root 11, which becomes 3 root 11. This is a very quick recap of everything that we did from National 5. Work through these questions, there are loads of them, but as I said, you have to be an absolute expert with them before we move on with this chapter. Good luck, any problems, let me know.